So yeah, hi, I'm Noah. I'm co-founder and chief product officer at Oasis Labs, and I'm going to talk about using blockchain as one element of a new approach for protecting data privacy. So I'll explain exactly why blockchain solves some key problems for building a secure data market and how other techniques are needed for a full solution. So everyone knows data is extremely valuable, especially when combined with analytics and machine learning. Data can provide enormous societal value across many industries. But there are a few major problems with data collection and use today. So the first problem is users are losing control of their data. Companies are collecting more and more data about users. And once they collect the data, they often misuse it by selling it or using it for purposes that users might not be comfortable with. And the fundamental problem here is that once the data is collected, the user has very little transparency and often only learns about this misuse after the fact. Then the second problem is that today most of the valuable data is siloed. This is often because of privacy concerns, but also because companies that collect the data often want to retain a monopoly. And so as a result, the data is not shared and therefore not used for its full potential. So why does this matter? Let's take a specific example of medical data. So if patients were able to share their data with healthcare professionals, this could lead to dramatic improvements in patient care. Now, if they were also able to share their data with researchers, this could have enormous benefits for improving medical outcomes. Now, an ideal solution would let the patient directly share the data themselves. The user might not want a large company intermediating because of exactly the issues I described earlier, and because the user should have the right to decide who they share and don't share their data with. It shouldn't be up to a company to decide who to share a user's data with just because they happened to collect it. So this is just one patient. If you think about how an approach like this might scale, there might be multiple patients across multiple different hospitals. The researchers themselves might want to collaborate. And so the model we'd like is some type of marketplace or exchange that can easily facilitate this kind of sharing, and ideally do so in a way where the user still retains technical control over their data. Now, there are companies that are trying to do this today. The way they work is data providers upload a copy of the data, and then people who want to access the data can pay to download it. Unfortunately, today's data markets don't address the issues I mentioned earlier, and that's because once the data is shared, there's just a copy of it floating around out there. So that means the user has no technical ability to limit its use or audit how the data is being used. And so this means the data could still be misused, and the user oftentimes wouldn't even know it. And so the result is a lack of trust and therefore very little usage of existing data markets. Okay, so what would a better solution look like? This is one approach, and we call it a secure data market. So the way a secure data market works is the user uploads an encrypted copy of their data and defines a policy that specifies exactly how the data is allowed to be used. And the combination of this encrypted data and the policy is called a data capsule. So the data capsule is uploaded to the secure data market. Then someone who wants to access the data can write a program to operate on the data and upload the program to this secure data market. Now, the first thing that happens is the program is checked against the policy to make sure that it's only using the data in ways that the user allows. And if that's the case, then the program runs on the data. Now, ideally, the program will run in a secure environment that can guarantee that the data won't be leaked, and I'll talk much more about this in a moment. The program outputs some results, which are then returned to the data consumer, and the user's data never leaves this secure data market. So the advantages of this kind of approach are that the user still maintains technical control and privacy at all times, and that's because this policy is always checked and enforced before allowing access to the data. The nice thing about this is it still allows data consumers to use data in ways we'd like. They can still get insights from the data by running analytics and machine learning. And because the data consumer never gets a copy of the data, they can't possibly misuse it. And in fact, they can prove to the data provider, the user, that they're not misusing it. And in fact, certain data consumers might prefer a model like this because they don't bear any responsibility now for having to safeguard the data. So there are many challenges to actually building something like this. The first is how to automatically enforce diverse policies. The second is because we want to make the data useful for the data consumer, it means we need to support all the different ways that they might want to use the data. This means general purpose analytics and machine learning. The third challenge is making sure that whatever results are returned by the program are safe for release. It would be a problem if the data consumer could just download the user's data in the results or return some results that might violate the user's privacy. And I'll speak much more to this later. You'll see information can be leaked in results in unexpected ways, so one needs to be careful about this particular risk. And then finally, we would like to require minimal trust on the data market. We want to ensure that the data can't be viewed even by this data market, and that policies are always enforced, and there's no way to circumvent them. And this piece is really important. If we didn't have this, and the data market was operated by some large company, and we had to trust that that company would only use the data in ways that the user allows, we'd be right back at square one, right? This is exactly the status quo that we're trying to change. So speaking of these policies, we would like to support a range of different policies that cover all the different restrictions that a user might want to impose on their data. And this includes where the data can be stored, who can access the data, how the data can be used, even by people who are allowed to access it, and then what types of security mechanisms need to be used in order to safeguard the data. So the hope is that if the system can support these sorts of restrictions, then users should feel comfortable using this kind of system. Because even though the data leaves their machine, they can still assert control over exactly what happens to the data. OK, so how could we actually build something like this? There are really three core technical building blocks that are necessary to make this all work. So I'll talk first about what each one provides, and then I'll show how we can combine them together. So the first thing I'll talk about is blockchain. Blockchain technology provides two very important things here. The first is smart contract execution. So smart contracts effectively act as a trusted third party for transactions. And these transactions can be very general. Smart contract is just a piece of code. And what blockchain guarantees is that this code will execute correctly. So we can use smart contracts to enforce the policies and manage access to the data. And in doing this, we can ensure that parties that might not trust each other, like the user and the data consumer, will have assurances that their interaction will only happen according to the rules defined by the smart contract. In this case, meaning the data will only be accessed according to the policy. And blockchain, of course, allows us to provide this guarantee without requiring either of them to trust a single central party. And then the second thing blockchain provides is a distributed ledger. So it can store a log of any type of transaction. And blockchain gives us the guarantee that once this log is written, it will be available, it can't be censored, it can't be modified after the fact, and that no single machine on the network can break these properties. And so we can use this feature to store a log of data access and a history of what's been done with the data. So this provides an audit trail that the user can inspect at any time. And so this essentially provides transparency for users over exactly what's happening with their data, even as it's running on remote machines. So these are good properties, but what blockchain doesn't provide by itself is privacy. So in today's systems, all transactions and data are publicly accessible on the ledger, or at a minimum are accessible to the machines that are operating the network. So you couldn't directly run a data market on today's blockchain platforms, or you would have to trust that all of these machines wouldn't steal the data. And remember, we want to minimize that requirement. And so we need to combine blockchain with other technologies if we want to make this data market both decentralized and secure. And so that brings us to the second component, which is called secure computation. So secure computation essentially emulates a black box in which computation and data run. And this black box is often called a T, or trusted execution environment. So the program and encrypted data go into this black box, and the only thing that comes out is the result of the program. So essentially, the decrypted data never gets viewed. So we can use this technique to make sure that user data is only ever processed inside this black box, meaning that machines that actually run the computation can never see the underlying data. All they can do is produce the result. And then the final component is called program rewriting and verification. The basic idea of program verification is that it takes in a policy and a program, and it outputs an answer either yes, this satisfies the policy, or no, it doesn't. And most of the work in this space is focused on how to do this automatically and to do this for a diverse range of policies and programs. And there are ways of doing this that are guaranteed to be sound, meaning if the verifier says yes, one can generate a proof that the answer is yes. And this class of techniques can also be combined with program rewriting to automatically transform the program into one that is guaranteed to satisfy the policy before it gets verified. So these are the three pieces we need. Blockchain technology automatically enforces the policies through smart contracts and provides a decentralized log. You can think of blockchain here as just the orchestration layer that connects all these different pieces together and makes sure that all of them run correctly without relying on any central party. Then secure computation is added to the computation step to protect the data from the machines that are running the computation. So the data market can still make use of the data by running the programs and machine learning without exposing the data. And then finally, program rewriting and verification can automatically verify and enforce policies for untrusted programs. So this means the data provider, the user, can just focus on writing their policy. They don't need to worry about whether the data consumer will voluntarily comply with the policy. They don't even need to worry about what the data consumer is doing. They just need to define in their policy how their data is allowed to be used, and program verification will ensure that the data is only ever accessed according to those restrictions. So hopefully you can see how these technologies all complement each other. So let's put this all together towards a secure data market. The way this could work is the data provider uploads the data capsule, and this is recorded to the ledger, and the data capsule is encapsulated by a smart contract that defines interfaces for running a program on the data through which the policy verification happens. Then a data consumer can upload an analytics and ML program, and then this could be expressed as a smart contract. This smart contract will call into the data capsule contract saying, I want to run this particular computation on the encrypted data. Will you let me? Program verification inside the data capsule will check what's being done and compare it against the policy. And if it can prove that the access is allowed, then it will write a log to the ledger that says this user's data is about to be used for this particular purpose. It's going to be accessed by this data consumer. Here's the computation that's going to run. And then, and only then, does a trusted execution environment get instantiated, and the program and the data go inside this trusted execution environment. The program runs, it computes some results. Those results can be recorded back to the chain. The data consumer smart contract can be updated with those results. And then depending on the policy, the data consumer can query the results. If this was a model, there might be interfaces for serving inferences on the model. The policy might say that the data consumer is allowed to download the model. This could be up to the data provider how they want to allow even results of their data to be accessed. And of course, the data never leaves this secure data market. And through blockchain and smart contracts, we can do this all without relying on any central party. So the entire system is decentralized. So that's a very simple architecture that solves some of the fundamental challenges I mentioned earlier. In practice, there are extensions you might want to build on top of this to make the system more practical and to align incentives between all the parties. So for example, a data registry could allow data consumers to discover data sets and combine them together. Data validation could be used to make sure that any data that's uploaded is valid. If the policy restricts who can access the data, then this needs to integrate with some identity management system. There's a lot of great work on decentralized identity on blockchain, so this could hook into those systems. And then incentives, if you want to incentivize people to use this system. One of the nice things about building this on blockchain and taking advantage of the existing blockchain ecosystem is that this makes it very easy to incorporate tokens or cryptocurrencies into the data market, for example, to pay users for contributing their data and allow them to get value from the use of their data. And then if you're incentivizing people to contribute data, oftentimes you want to ensure that you're properly compensating them, so you want to know how much data is worth. And there's some interesting research that attempts to automatically calculate the value of data based on how much that data improves a model. So all these things could be incorporated as optional components at the application layer. So let me talk briefly about the technology and the work that's been done behind these building blocks. Because of time, I won't be able to get into all the details, but I can give some of the highlights. So I assume most people are familiar with blockchain technology. I won't get into that. The secure computing So I mentioned secure computing acts like a black box. So how exactly does this work? There are a number of different techniques for providing this black box execution. And all of these techniques have different trade-offs in terms of their performance and what types of applications they can support. So secure hardware is one way of achieving this through the use of special features in the hardware itself. And one of the most well-known implementations of secure hardware is called Intel SGX. And it's built into Intel's CPUs. Now, unfortunately, SGX has some well-known vulnerabilities. So this suggests that the current technology is not yet at a point where it can be completely relied upon, but the industry is moving towards more secure designs. And one of the efforts towards that goal is called Keystone. So this is a fully open source design for secure enclaves. And this is a collaboration between Berkeley and MIT. And then there are cryptographic techniques like multi-party computation and zero-knowledge proofs that are nice in that they don't require any special hardware. On the other hand, they're quite a bit slower and only work for limited types of computations. But there's been a lot of great work recently on making some of these techniques more practical. So all these techniques have different threat models. No single approach is strictly better than the other. They all come with different trade-offs. So depending on the deployment scenario and the set of computations that one wants to support, the data market could choose to leverage any one of these techniques, or they could leave it up to the data provider to decide which one needs to be used. The architecture I described earlier is mostly agnostic to the specific technique that's used for secure computing. Then the other component I talked about is program rewriting and verification. And there's a lot of literature on how to do this. The techniques differ based on what types of policy languages they can support, what types of programs they can handle. To take a concrete example, I'll focus on a policy that attempts to provide guarantees to the user that their privacy will be protected. So this is actually a harder problem than it might appear on the surface. And to illustrate that, imagine the data scientist is submitting these two queries. The one on the top asks, what is the average blood pressure of patients over 50 years old? The one on the bottom asks, what is the average blood pressure of patients named Joe, aged 55 in Santa Clara? So the one on the top clearly reflects a trend. The one on the bottom very obviously violates Joe's privacy, so we wouldn't want to allow that query. Now, the question about what to do with the query on the top, at first glance, one might say, because this reflects a trend, clearly it's safe to run. But if it so happens that Joe is the only person in the data set that satisfies this condition, then the top query is actually equivalent to the bottom query with respect to whether Joe's privacy is protected. So we wouldn't want to allow this query. So the takeaway here is that even statistical queries can leak information and violate privacy. And the extent to which they violate privacy depends on both the query and the data. So if we want to provide strong assurances to users, then we need to reason about these sort of risks very carefully. There is some work that attempts to solve exactly this problem. One of the techniques is called differential privacy, and I'll explain that in a moment. So it turns out this risk of information leakage in results also applies to machine learning. So there's been quite a bit of work that shows this. This is a particular paper that shows that a deep learning model that's trained on sensitive data can allow someone that is just querying the model to reconstruct sensitive information from the training data, including credit card numbers and social security numbers. And this happens even for otherwise well-behaved models. This isn't even a degenerate case. And this can happen inadvertently as well. And so one needs to mitigate against this. You can use differential privacy to solve this problem as well. So I talked about differential privacy. What does it actually provide? Differential privacy is a mathematical definition of what it means to have privacy. So it's a very rigorous notion of privacy. The definition intuitively says that if you were to take any query and run it on two databases that differ only in one user's data, then the results, if it were run on those two databases, have to be essentially the same. So this means you can't tell just from the results whether the query ran on database 1 or database 2. So if this property holds for every user and every possible database, which differential privacy says it has to, then that means that users have very strong guarantees of privacy. Because looking at the results, there's no way to learn anything about them because the results would have been the same if they weren't in the database. And so a lot of work in the space is building algorithms and systems for satisfying this definition in a practical way that works for general analytics. So there's been some work to deploy differential privacy in industry. Apple and Google are using differential privacy in some of their systems for telemetry to collect user data. In some of our previous work, we built some techniques for enforcing differential privacy automatically for SQL queries. And this particular system has been deployed at Uber for internal analytics as part of their GDPR compliance efforts. And there are pilots underway at other organizations. And then in follow-up work, we showed how to do this with machine learning models. So all this work is open source. It could be integrated pretty easily into a data market as part of the program verification and policy components. So in summary, the advantages of a secure data market over traditional data markets are privacy. The user has guaranteed enforcement of these privacy policies. Control, the user gets to define the policy and have guarantees that it will always be enforced. They can potentially change the policy later. They can revoke access. And because there's not a copy of the data floating around on the internet, it means that when they make those changes, they will actually be enforced. And then finally, the use of blockchain provides transparency and auditability by writing all accesses to this log. So before I conclude, let me talk about a real-world use case that's built with many of these techniques. And this is Kara. And it's a data market for medical data. So it tries to solve the problem of siloed medical data that's hard for researchers to analyze. So the way this works is a patient scans their data. In this particular pilot, they take a picture of their data with the phone. But in a production deployment, you might imagine this integrating with EMR systems. Once the data is captured, it's uploaded to this data market through a data capsule. And then researchers that want to train models on the data can upload their model into the data market. And the model runs on the data. The patient gets tokens as compensation for contributing their data, and the researcher gets their trained model back. And because this all runs as smart contracts, the patient doesn't need to trust the researcher. They don't need to worry about what model is being trained. Through differential privacy, they have assurances that whatever's happening with their data, their privacy will be protected. And of course, this all runs inside of a T, so the patients know that their data can't be leaked or stolen, even by the machines that are running the computation. And there's a pilot underway through a collaboration between ETH Zurich, Berkeley, and Stanford. So if you're excited about these ideas, if you want to go and build a secure data market or any other application that requires privacy, Oasis Labs launched our DevNet recently. It lets you write smart contracts and run them inside of a T. So you can go to our website, oasislabs.com/developers, to learn more information. If you want to get involved in the Keystone project, this is the open source effort for secure enclaves. You can go to their website. And Oasis Labs has a fellowship to support research in many of these techniques I discussed. So you can go to oasislabs/fellowship for more information. So I hope this gives you a sense for how blockchain and other privacy-preserving technology can be used for what I think is a great societal good. And I hope we can work together towards building more of this technology that can protect user privacy while getting more value out of data. So that's it. Thanks very much.